Okay, I think we can safely start. So let's start by quickly recalling what we did last time. Recollection. So we finished by introducing a Stratonovich or a Stratonovich-Fisk Stratonovich integral, which goes as follows: for function f of this type, bounded derivative is a bit of overkill, but whatever. And stochastic process, such as stochastic process admits a representation of this form. A of t, just of t. It may depend on psi in any manner. TV set integral from 0 to t f of psi of t in the sense of Stratonovich by introducing a p limit or L2 limit. It depends. We work in L2 limits effectively, but the whole theory of stochastic integrals is a theory of limits in probability. We just don't really consider such extension of all calculations. Which this was true for the eta integral. This is true for the Stratonovich integral, for obvious reasons. So this is the limit of such expressions. It can be written in terms of eta integral dws plus a correction of this form. It includes derivative sigma as ds. Here t and k is just k divided by n. T capital, or in our case just t small, and w, delta w and k is just w t n k plus 1 minus w t n k. This is a notation that I will use in the following subsection too. Let us formulate a theorem that also explains some more advanced properties of this integral and also introduces an alternative way of defining such integral. And quite often, this is the way you will find in literature. For Wiener process, for good functions, they are equivalent. By general, if you try to do Stratonovich integration with respect to more general processes like semi-martingales, this is a proper definition. The second definition is a bit more restrictive. So the theorem will consist of 3, I think, points. And I'm not going in this section to give full proofs. We will just discuss some intuition. Because introducing Stratonovich integral fully formally in a fully rigorous way would require some calculations that are quite repetitive in terms of what we already did for eta integrals, and overall Stratonovich integration is more of a digression for our course than an intrinsic goal. So firstly, one can do the analog of the eta formula. But for that, to introduce the analog of the eta formula, we can define just look what happens if we have our function dependent also on S and not only on the space variable, then we have pretty much the same relation between Stratonovich and Ito integrals. And I will write it still for only functions of this form, the Ito formula. Stratonovich integrals goes as this. So formally, the Stratonovich integration doesn't include correction terms. Some people would say that this is a reason why physicists like this integral, because it's make it easier to write some models for them, significantly easier. You didn't need to do corrections, etc. And overall, Stratonovich integrals often appear in physics, and they often appear in differential geometry. And in cases where you have some commutative structures of your vector fields that are used in your model, because by introducing some algebraic structures, some calculation with Stratonovich integral also became easier to do than with Ito integrals, and this is a natural choice. However, in terms of another advanced techniques such as martingales and related techniques, the Stratonovich integral is not a martingale, so it loses very important properties. It is quite efficient. And now here is an alternative definition of, again, I will take a function as bounded derivative, and then Stratonovich integral can be obtained as a limit of this type. So instead of averaging over values, sorry, okay. Here, we're averaging over time. And in fact, one can do even continuous averaging over all times from t and k to t and k plus 1 in some manner. But it's a bit outside of the scope of our discussion. So again, since we are not going to give full proof, let's discuss only the intuitions that explain why this limit is going to coincide with the previous limit. So let us introduce a middle point of our intervals from our partition. And then let us consider the errors that appear between these two integrals. So I'm going to consider this minus xi t n k. Yeah, I think it should be k plus 1. Or just k take. Okay, so this is by the Ito formula. So if you consider now multiplication, the result of multiplication of this expression by delta w and k, this will effectively give you two terms, t and k, s and k, a of r dr plus integral t and k, s and k, sigma of r dwr. So now when doing the summation of all such stuff and multiplying with f prime in the sense of limits, sense of sums and limits, we will effectively get T N K S N K sigma R D W R W S N K W T N K plus T N K S N K W D W R now. Why I forgot about this term? Because this is formally has an order 1 over n to the 1/2, and this is has order 1 over n. So this is has order of -3/2, and this shouldn't affect the resulting sum when everything is good. And now this part is going to give you the real correction, because we integrate over t and k to s and k, but this part does not contribute to the result. Why? Because we integrate over no disjoint time interval. So effectively, to understand why it's true, introduce such two t and k and k, and then sum, mathematical expectation of sum from k to n, from 0 to n minus 1 delta 1 nk delta 2 nk, even if squared, it just goes to 0. This is a calculation that can be verified quite easily. So if you compare this and what happens here, this disappears, and this, when you use maybe I should have considered here the difference in t and k plus 1, but overall the calculation goes exactly the same. You will in the end get rid of that, and you will get a correction of this term f prime sigma r s, and the sum of f t and k delta w and k is going to converge to just the ordinary f dw, which is the first part of this representation of Stratonovich integral. Overall, the problem, because we have here, this gives you 1/2 to the correction, this just disappears. So this is an idea. I don't think it's worth discussing more. Now let's return to the original question. So we were discussing the following question. If we have a sequence of processes of bounded variation, 0t, and such that they converge to a Wiener process in some sense, for instance, in supreme norm, they can be thought as linear approximation of the trajectory of Wiener process that we get from our observations, for instance. If what happens to solution of the corresponding differential equations, stochastic differential equations. Can we recover the original stochastic differential equation by considering such approximations instead of going through the whole machinery of Euler-Maruyama and other schemes? And the answer is no, you cannot. You will recover the Stratonovich integral. For that, we will need like three results. Let's quickly discuss them. So the next theorem is typically called Doss-Sussmann method, effectively. And it goes as follows. This is a rare example when stochastic differential equation can be solved explicitly. Because in most cases, solutions to stochastic differential equations appear as byproducts of some other research, and then people gather them. But overall, it's not really feasible to prove anything, to establish some representations. There is no such vast variety of methods of finding explicit expressions for solutions as for ordinary differential equation. So the process dxi of t here stands integral, and now I am writing this as in a differential form, but obviously we know that this can be rewritten in the form of the integral and then solved under this condition of coefficients. It has a unique strong solution. This process admits a representation xi of t just equals a function that depends on wt and x of t, where f is a function from r squared to r, continuous. We will write down this function in terms of some ordinary differential equation. X is a solution of one stochastic ordinary differential equation. So how is this possible? So this is step one. So the idea of this transformation is to consider an analog of the original equation, but for some good function, even with bounded variation, possibly, find the solution and plug in W instead of this placeholder beta to obtain psi. So this is the idea. And it works. So to solve such equation, one does this as follows. One considers the following ODE, sigma f xy So for fixed y, we consider this an ordinary differential equation with respect to x. And because sigma is good, it's continuous and it's effectively has linear growth. It has a unique global, so has a unique global solution. So recall, so for ordinary differential equation, to have a local solution, you need just this coefficient to be continuous, but to have a global solution, you have a restriction on the growth. Because what bad might happen is that the solution can blow up in finite time and the growth restriction forbids it. Is global solution. We don't know like the explicit expression for it. It depends on sigma. But then dy dx f x x is just dx dy f and prime dy f and dy f at time x equals 0 is just 1. And this can be solved because this is now a linear equation with respect to dyf. So dy f xy is dy f 0y, which is just 1, exponential. Is it? This is first. And step, oh, sorry. The second additional differential equation we need is going to be is going to require the following additional construction: xy. And then we need to establish that this function is good. And for that, we need to prove the following claim. So for any c greater than 0, there exist some constants that depends on it, such and the following gross condition holds also for any y and x less than c. So we have like local Lipschitz continuity and local growth, linear growth. So to do this, let's proceed in also steps. There exist c, another c again, a universal constant, the value which may change from line to line, less than maximum this is because this is bounded. This implies that a f x y is a, let's write this as composition, x2 is less than, because a is Lipschitz continuous by our assumption, this is less than the constant from the minimum of these two values to the maximum of these two values, modulus the alpha, and this is less than c x again, because we just established the previous. And now we need to also say something about the denominator in the expression for f small, because it's a product of two functions. The first function is already Lipschitz locally in terms of x, and this is less than supremum over all y dy 1 dy fxy modulus gained by the Taylor formula is just equal supreme over all y's dy. I'm taking the derivative of this expression, and here just says integral for modulus of ez and another internal derivative because of this property. Maybe I did some mistakes, but I don't think so. Overall, it's going to satisfy x because we have an additional integral. We have estimates on these expressions, and we have this. Like dy. So this is going to give you this expression, the derivative of the internal, which is derivative. It's going to give you the second also derivative of sigma here, and then the derivative. Here, C capital is the bound on the second derivative of sigma. But overall, this gives you the claim. Now we can move forward. And here we get, I think something like that. Let us consider Wt x of t. So for fixed omega, this is just a number. So this is an ordinary differential equation with a random coefficient. Again, there exists unique global solution. Why it's unique and global? Because it's locally Lipschitz continuous and locally at most linear growth, so it doesn't explode even locally. And now we can define our psi of t to be equal f w of t x of t. And now we can check that. What we have here, dx f w t psi of t dwt. So this is essentially zeta formula. Wt x of t dx of t. Plus correction. Don't forget that we need to do corrections. Since x of t doesn't contain a stochastic integral, there is no correction with respect to the second derivative with respect to y, and there is no mixed derivative. We will also, I hope, see similar calculation today in a slightly different setting, dt, which is this gives sigma dwt, because this is how f capital was defined, plus this dyf, dx is f small, dt f small is exactly a of f divided by this dt plus 1/2. And this is the second derivative of the expression, so this gives sigma dx f dt. This is gives sigma dw plus a of f dt plus 1/2 sigma, and this is again sigma dt, which is exactly the Stratonovich integral. So this is indeed a solution. Now let's quickly formulate a proposition that explain why you can even consider such expressions. Because obviously integrals with respect to functions of bounded variation is a known thing, but differential equations with respect to them, not really. So I consider a process beta, which is continuous. and has bounded variation locally on this interval, and functions a sigma, which is Lipschitz continuous. Then d psi of t equals sigma psi of t d beta t plus a psi of t dt, where this is just a Stieltjes integral, so Riemann Stieltjes integral, effectively. Just Riemann Stieltjes, not even the Lebesgue Stieltjes, has a unique solution. Let's very quickly sketch the proof, just sketch the proof. So again, one uses subsequent approximations, pretty much exactly as we did for stochastic differential equation, as one does for ordinary differential equation, unless one wants to apply something like the contraction principle, and this is defined. Now let us define delta n by the difference psi n minus 1, and let us do pretty much the same that we already did once in our life. S less than t delta n s is less than, because of this representation, this cancels because we have a difference, everything is Lipschitz continuous, so this gives some constant, the Lipschitz constant, the maximum Lipschitz constant for A is sigma, and this is supremum over R less than S delta n R ds plus delta n R dws, where v of s is a variation of beta on 0s. So this is the standard property of Stieltjes integral. So this variation of beta over 0s. And now it's pretty much clear that iterating this, we will arrive at another constant Cn t plus to the power n factorial, which immediately gives us the conclusion, because this series is convergent, and that technically proves that this is Cauchy sequence, that's a fundamental sequence in C0t small for any t, for any fixed t small, because the integral, the series with such terms are convergent, so supremum over nm going to infinity, psi ns minus psi ms can be estimated in terms of this series goes to 0 and nm goes to plus infinity. You can check the following, the corresponding calculation for stochastic differential equations. So it means there is a limit. There is psi, which is continuous on the whole half line, and for any t psi n converges to t uniformly on 0t. Now passing to the limit gives you that psi is a solution. And using exactly this calculation, a very similar calculation to the one that was able to get us this expression, we can prove that, I believe, the next psi is a unique solution. I consider difference and use some Granola-Bellman is a unique solution. So we indeed can consider those approximations. And now we are ready to formulate at last our theorem that if we have function is bounded derivative, A is Lipschitz, if you have a sequence of processes is such that they are bounded, have bounded variation, and let's say continuous, and converge W, some Brownian motion uniformly, which is going to happen with, say, as I say, linear approximations, linear interpolations of Brownian motion based on a finite number of observations. Then solutions of d psi n of t equal a psi n of t dt plus sigma psi n of t dw n of t converge to the process that solves a Stratonovich SD. Note that this is a one-dimensional result. It can be done in a multi-dimensional setting with some additional reasoning, but it does require sigma and a to be autonomous, that is, to not depend on time variable. Let us again quickly go over the proof. So step one, we will take the same f capital and f small. So this also, and let us consider d say y and t equals to f t dt and set psi n of t is f w n of t y n of t. So psi n is a solution of the original equation here. This is pretty much what we established already, but again, you can check it one more time. So instead of speaking about comparing psi and psi n, we will speak about comparing yn and the corresponding x that appeared in the proof of this result here. So because we have the same function f, we have wn instead of w, and we have yn instead of x. So we now can compare them instead of comparing the solutions. To do this, let's do some localization in the following sense. We will use localization as Granola-Bellman. Let Cn be the Lipschitz constant for phi small. It's locally Lipschitz, not globally Lipschitz. And let epsilon be such that t epsilon squared, so we also fix t. We can just consider t capital. and tau n that ws goes, the first time ws goes above n minus 1, or ys axis from the previous proof goes higher than. So here x is such that our psi of t is equal f w of t x of t from the previous proof. So effectively dx t dt is f small wt x of t. It was constructed. And also introduce delta n small n capital. This is infimum, if such infimum exists, of those s, the wns goes above n capital, or yn's goes above n capital. There is a bit of a discrepancy here. We will see why we need asymmetrical definitions. Then the following chain of event happens. This probability one, we work in this probability one. This is a rare example, but SDEs are considered for fixed omega, effectively. This is some number, so for all numbers greater than this, two things happen. Supremum x, this is x, is less than epsilon squared for all s less than tau and minimum theta and n. Why? Because f is Lipschitz continuous locally. That means it's uniformly. Well, it doesn't even need to be Lipschitz continuous. It's just continuous function, uniform. It's continuous function, so it's uniformly continuous locally. And before these times, all these processes live on a compact. So eventually this happens if these became very close, because this is for fixed omega, this is just a number. Why I can use the Lipschitz continuity? Because we established the Lipschitz continuity with respect to second variable, considering the first one as a parameter. And supremum wn of s, and s less than, again, this minimum is less than n, which happens because w doesn't go above n minus 1, so this doesn't go above n, at least at some point. That's why we need this difference in definitions for tau and theta. So let us compare now s minus xs. I messed up notation, I'm paying a price for it. For s less than tau n, again minimum theta and n. This is less than, by definition, what these things are. This is the difference of two integrals. Now let us do the triangular inequality. dr flows from s f w and r, y of r minus f w of r dr. So this is the term that was subtracted and added. correspondingly. And now this is less than, because of step 3, t capital epsilon squared, because here we have this, again, x, not y, but x. Plus Cn integral from 0 to s y and r minus x of r dr. So the Granoll-Bell immediately allows us to conclude that the difference is less than Cn t capital epsilon squared, and we chose epsilon so small that this happens. For all s here is probability 1. From here we can conclude that tau n is less than theta n. Because wn and w are close, so are yn and x. So before this happens, this must happen. Before reaching for the second elements of their corresponding pairs, the level n, the first elements of their pairs must reach n-1 at least, for sufficiently small n epsilon. So the limit, let's write it, supremum s less than tau n theta nn. So it's just supremum less than epsilon. Epsilon is arbitrary. Okay, this is x. Let's just equals 0. Now, by taking this go to infinity, and why this goes to infinity? Because for fixed omega, all the processes we consider are bounded. So obvious tau n is going to infinity, or to more precisely to t capital. Just give us conclusion. So this answers the question. If you consider alternative way of approximating to stochastic integrals by considering, let's say, observation of a linear process of fixed point of times and doing linear interpolation, you do not recover the original SDE. You do recover the Stratonovich SDE, however. So it's not a waste. It's actually good. Now let's do, I think, the most interesting part. Let's start the most interesting part of our course. So recall that we said that we are going to consider 2 tasks. The first task was about approximating the solution by some Euler-Maruyama or Milstein, etc. And the second question was, how do we calculate something like this? Because sometimes you want to model the behavior of the whole process to see how it behaves in terms of heating levels, etc., etc. Sometimes you're just interested in what happens at the terminal point of time here. Moreover, this has a very important application in theory of partial differential equations. And what is interesting, to even establish a rate of convergence, even for Euler-Maruyama and for Milstein equivalently, you actually need to exploit that connection between partial differential equation and stochastic differential equations, and this is essentially what we're going to do. We need to introduce those connection to discuss its symmetry, try 2 different directions of this connection, and conclude our course with establishing the speed of convergence in such approximation. So what approximations are we talking about? We are talking about the Monte Carlo method. Monte Carlo method, which means so we simulate independent copies of approximate of an approximate value of psi of t, and we take psi of t by averaging the error of such approximation is obviously is given by this decomposition. Eta 1. This is the essence of the Monte Carlo method, because by the law of large numbers, this is convergent to this expectation. And plus the statistical part of the error. So plus non-linear stuff, which is typically ignored, and it includes something like pseudo-randomness of generators of random numbers your computer is actually using. It's not using real random numbers. It might try to use a random seed, but the sequence of numbers that you used in this Markov chain, eta 1, eta n, and even to simulate eta 1, eta n, you use an internal Markov chain. Those numbers are not really random. Unless it's almost never random, unless you're speaking about cryptography, where people going through a really hard work to get good pseudo-random, or even try to get really random numbers, but using some hardware. Overall, one can try to use seeds like later digits of CPU time or something like that. They're pretty random. So we have independent copies, and let's say that eta 1 and eta n capital are obtained by the Euler-Maruyama. Each Euler-Maruyama is essentially a finite Markov chain, by the way. So this is a statistical error, and this is the error of the Euler-Maruyama scheme in this sense. So this is the error of the scheme after averaging, and this is a statistical error. Now, discussing statistical error is outside of the scope of our course. I will just give you a few hints. Statistical error. So to estimate them, typically it is advised to use something like Berry SN inequality, or some generalization or alternative versions of these inequalities, or concentrations of measure, or something like that. So I will just quickly recall you what sometimes of these expressions are. Or concentration of measure. If you're interested what concentration of measure is, I actually have a lecture devoted to that subject and aimed at students, like really graduate or even undergraduate students, that should be on this YouTube channel. This was a few years ago. It starts from basic stuff, and we go even to have a glimpse of functional formulations. So the very essence inequality. I'm not going to discuss the proof or something like that, because the most general form is actually a very hard result. It's very recent. If you have independent copies of the same random variable, it's finite. Third moment, then supremum over x, probability is the sum fluctuates away from its mean, the mean of all these variables, can be approximated in the terms of just Gaussian distribution with the error that has a uniform bound of this type, n variance psi 1 squared. Obviously, in practice, you do not know this variance, you do not know this, so you might try to run a simulation to actually estimate them, or to limit them by using some other reasoning. Sometimes it's possible, sometimes it's not. Then effectively you will be using some empirical estimates to estimate this, which kind of works in practice, even from my limited experience with such expressions. I want to also recall the so-called Bekele's inequality, because not many people know about it, which is strange. It's a version of it. It has many versions. By the way, this 1/2 is a very recent result. It's like maybe 15 years ago. It was like 1 over 1.7 or something like that before that. The Bekele's inequality is interesting in the sense that it gives you a non-uniform bound. Because obviously, in most cases, you do not care about something that happens for really large x. And this is again a constant, 1 from x to the third power, and exactly the same expression here. Psi 1, 3/2. Now, we don't really have time to discuss concentration inequalities and even to formulate them in the forms that might work here, because it's actually quite a lengthy discussion, how they appear. We can formulate them, but to discuss how they appear in this scheme is a lengthy discussion. But overall, this is a different problem for estimating this. Note that, remark, we already know, for instance, for Euler-Maruyama scheme, we have the estimate psi t minus eta 1. We already know that this is less than constant n to the power 1/2. And one can say, well, if f is Lipschitz, then f psi t minus f eta 1 is actually less than some constant n minus half. Immediately. But the problem, this is a rough estimate, and one can go much better. Again, the reason is because we don't really want to replicate the behavior of the whole trajectory. We need to replicate the behavior on like a terminal point. So the next big part of our course is PDEs and SDs. This is what we are going to do till the end, with some digressions towards properties of SDs and differentiability of flows generated by SDs. So the intuition, I'm pretty sure you know where it's all going, but still, let us consider just one-dimensional Brownian motion W. Then, given, say, W0 equal to x, we can define the function psi t, wt, which is just the integral of r 1 over dy. People sometimes use notation fwt given w0. Note that this is not really a conditional expectation. It's just an indication that this is true. It's not like w0 is a random variable in this formulation. No, it's not an event. It's not a real conditional expectation. It's obviously going to have the same form if w0 is a random variable, but it's a bit of redundant in this setting. And we can trivially check, like really trivially, that dt minus 1/2 of the second derivative uxt equals to 0, and this is true. The same is true in multidimensional setting. At effect dimensional setting, no, dt minus 1/2 Laplacian uxt equals to 0, and ux0 is still f of x. Now, you can do this, and I will give you this an exercise if you want, by simply differentiating such integrals with respect to a parameter. It does require some calculations, so it's not like... But effectively it's immediate, if you know the property theorem. So there is a relation between such expressions and partial differential equations. And this is an example of a very deep connection. This connection is asymmetrical. And one can also say something, need to say something about this connection in relation to numerical methods. Because if you speak about numerical methods for partial differential equations in real life, and you look at this expression, this is what is called a classical solution. This is its function. This is going to be twice continuously differentiable with respect to special variables at one time continuously differential with respect to time, and that satisfies this in a proper sense. But most numerical methods that are actually used in more or less advanced PDE studies are based on weak formulations. And typically that's the variational formulations that consider solutions in Sobolev spaces. So overall, if you think about using Monte Carlo to solve PDE, I'd say probabilists tend to overestimate the importance of Monte Carlo in this particular setting. It's very different when you think about something like financial mathematics, where you need to model your process. Then Monte Carlo is a very natural choice. However, for people doing PDEs, Monte Carlo or just algorithms for numerical solution of the corresponding PDEs with using probabilistic tools is very rarely a choice. They're probably going to use just something very known to them, something that is reliable and is guaranteed to work, like finite volume, simple cases of finite element, methods, etc., etc. So you shouldn't be expecting people in the PDE field to do a lot of Monte Carlo. Not really. However, from the theoretical point of view, there is an interesting possibility that such probabilistic representation, because it's a representation of a solution of this PDE in terms of a random process. There is an interesting amount of theoretical possibilities this representation can develop and can produce that are not really available by analytic methods. On the other hand, fully developing the theory of such PDEs from the probabilistic point of view is very rarely a choice. Like extremely rare. The reason because at some point while doing discussions of such expression, one falls into at least the sphere of semi-group methods. We are not going to discuss them, but this is generally what Kolmogorov's theory of diffusion is about, or Dynkin's theory of diffusions is about. Another interesting moment that we will see is that probabilities tend to impose conditions on this operator in a general setting that are very different from conditions that are natural from the probabilistic point of view. From the probabilistic point of view, if you think about strong solutions, you know that you already have only Lipschitz continuity. However, if you move to weak solutions, remember we have two statements about weak solutions: the existence, where we didn't really need it much, just continuity even of coefficients was sufficient. But the uniqueness part required the corresponding second order differential operator to be elliptic. This is the assumption from PDEs, not from probability. And this also shows that even in a fully probabilistic setting, to discuss something like uniqueness, you often need to go into the setting of analytical tools. So this is a very interesting fact that probability, in contrast to quite a few fields of mathematics, is not closed. To do stuff for very natural objects, you often need to use something very far from this probability, very far from outside the probability. So let's effectively start with proving some rigorous statements and investigating this connection. So we have a scheme, we have PDs, we have SDs. Let's consider what we can do in this direction first, because this is how it often goes in real life. So we will consider multidimensional stochastic differential equation of this form: psi of t dt plus j 1 to m sigma k j psi of t dw j of t. Here k ranges from 1 to m. W1, Wd are independent Brownian motions. And right now I don't assume anything from these coefficients except for them being for them satisfying standard A1, A2 assumptions. Lipschitz continuity uniformly with respect to t and linear growth. We need to introduce additional metrics because sigma is a matrix, not a square, but a matrix. Sigma transposed. So AIG is a sum over K from 1 to M sigma ik, sigma jk. So this matrix forgets about how many winner processes we used, etc., etc. Effectively, because we like sum over all those winner processes, we put them inside and forget. And we introduce differential operator sum from k1 to d ak xt dxk plus 1/2 sum from kj1d akg x of t and two derivatives with respect to xk and then xg, or more precisely with respect to xg and then xk. This operator is going to play a major role in our studies. Now, to formulate the result, we need, instead of this stochastic differential equation, to introduce a family of stochastic differential equations that start from different points and different times. More precisely, we also need to consider dxi xts, which satisfy a stochastic differential equation with respect to variable s, ds, plus sigma s dw s. So here A is just a vector A1, AD. dw is a vector W1, WD. Sigma is a dm matrix. This is M1, so this is a scalar product in Rm. This is one way to write down this expression in one line. So this is a vector valued differential expression. And S here is greater than T, and psi x, T is x. So we, instead of starting at 0, we allow ourselves to start at any t greater than 0, and every x belonging into Rk. Now, before proceeding further, we need to discuss what an SDE domain might be. Overall, if you want your stochastic differential equation to exist and to be solvable in domain, because, for instance, you do not have your coefficients outside of some domain. Let's think about some model from, say, financial mathematics that must be positive, produce positive processes, like some price. That means that coefficients of the corresponding model, coefficients of the corresponding stochastic differential model, are not even defined for negative values. But it's not really covered by the previous series, so we need to say something about what happens in this case and how we approach this problem. Overall, one can say that it's more natural when you have some restrictions on the domain, on the region where your coefficients are defined, and you do know what happens outside, and you not really care what happens outside, because, say, you assume that if price goes to 0, you are closed and everything is good forever. It's more natural to use martingale techniques and martingale problems, but it's still possible to discuss what happens in the terms of just stochastic differential equation. However, we need to discuss how we approach this. So assume that A sigma, this is a vector, this is a matrix, are given only in some subspace of, now some D of the form D prime. So we'll assume that we don't have restriction on time as usual. We just have some restrictions of space variables. And let us consider two cases. Case one. This is the most common and the most natural. Common and the most natural. So this D prime is a domain that is an open connected set. Connected set. So we just do not care what happens outside of the set, which is also a very physical situation because all real life PDEs that needs to be solvable in engineering have bounded domains. All containers are bounded, and it's quite funny to try to read some textbooks written for engineers because they actually tend to make fun of theoretical studies in the sense that quite a few results that are different to obtain and very problematic and effectively ruined the life of theoretical people doing theoretical studies are of no importance to people doing practical calculations. They don't really have those problematic situations and don't have straight like corners, etc., etc. It's always something like that. So they have more problems with practical implementations and instabilities of their algorithms than in some abstract problems with, say, potential theory. So assume that we have our coefficients only in an open-bounded domain. Now, note that the idea is to extend coefficients on the whole space and then say, we solve our SDE and stop when we hit the boundary of our domain. And what happens outside of it, we don't know, we do not care. Maybe we will do some reflection for more advanced setting. Maybe we just stop here. But overall, we cannot go outside because the original problem doesn't even include some formulation of all coefficients outside. So for simplicity, let us assume that for simplicity, let us assume or maybe I don't even need that. It's a setting. So then there exists a sequence d prime n of compact sets such that first dn prime lives in the interior of dn plus 1, and second d prime can be represented as a union. This is a very simple exercise. So effectively what we're going to do some exhaustion of our domain d prime by good d and dn plus 1 primes. One can say a natural equation, maybe if we are given our coefficients on a good domain, coefficients are good, we can just use some theoretical result to extend them to the whole domain immediately. However, because we have a function f of x, 1 over x, no smooth function in general, even smooth function cannot be extended from an open domain. So you cannot really, if the domain is open, you cannot really do anything about extending it. Maybe these A and sigma don't have any extensions. Now, A and sigma are well defined on each dn prime. Now, distance between dn prime is positive, strictly positive. So we can produce produce a smooth approximation A and sigma restricted to Dn prime in such a way that firstly, there exists a smooth function We already discussed how to do that when we were proving the Ito formula. You do the modification of the indicator. And because the distance between these two sets is positive, you can take this modifier in a proper way. Because recall, if you want to do a modification of some indicator that is a function of this type, and you do just modification, you get something like this. So if you want this, you need to extend your set and then do modification. So this smoothing doesn't touch the original set. So you need to play with some extending the original indicator, the original set, and to play with the size of your modifier. And then you can define an equal a fn and sigma n equal sigma fn. Now, this is a good functions. They satisfy all necessary requirements for the existence of uniqueness theorems. These are good functions. Now, on the whole, RD. Thus, the process for fixed n, d psi n of t equal an psi n of t dt plus sigma n t psi n of t t scalar product dwt has a unique strong solution. I will say this is just well defined. And by the localization results that we proved earlier in this course, and it coincides whatever with all psi m, where m is greater than m, up to the moment tau n, which is the infinity of those t small that effectively means this, which is just equal the infinity that this happens for the origin process. Dn. So up to the moment of leaving Dn prime, you effectively have all your processes coinciding. We do not speak about the solution of the original SDE with coefficients a and sigma. We speak about solutions of SDEs with coefficients that are defined on the whole space right now. And they are all compatible. That effectively means that you can, which means you can define a process psi up to the moment tau, which is limit tau ends, which is effectively the infinity those t that leaves the original or hits the boundary of the original process, or just capital if that never happens, such that the psi of t is equal a psi of dt dt plus sigma psi of t t d double t t for t less, effectively less than tau. Because for every t is less than tn, you just look what is the set of our exhaustions this process didn't leave, and you use the corresponding psi n. And it doesn't matter which psi n you use, because they're all compatible. So this is a definition of a stochastic differential solution, of a solution to stochastical differential equation for such conditions, for such coefficients, which are not defined on the whole space and defined only on the effectively open set. Note that it doesn't really explain what happens when we hit the boundary. So when this happens, if it ever happens. Maybe it never happens, maybe it sometimes happens. It doesn't, if you want to introduce something like reflection, this is an additional layer, because then you will need to define what happens after heating. So what happens after this time, if it's finite, etc. It's always finite, it's t, but it doesn't equal to t, or if heating the boundary happens at time t capital. But overall, you can produce examples of processes that never hit the boundary, etc., etc. We ran out of time, and next time we will very briefly consider a more artificial example when this d prime is closed, because this actually provides more benefits, and sometimes it provides interesting insights, but at the same time it has some interesting problems. But overall, this is a natural construction, and this is a construction that is typically used in the theory of Martingale problems, etc., etc. Does anyone have questions? About this construction, for instance? Because it's important that you see it. Okay, then see you next time with a brief continuation of this discussion and the Feynman-Katz formula.